Okay, we will get started. I'm Peter Yu. I'm a PhD student from MIT MCube lab. MCube stands for Manipulation, Mechanism, and at MIT. So Alberto Rodriguez is our leader for our team MIT Princeton. So this is the whole team. The MIT part mostly come from the MCube lab, and the Princeton we cooperate with Jen Xiong's group, the Vision group, and we also have researchers from ABB that we are very thankful that they provide the ABB arm and resolve some technical issues. So today's talk I will be mostly focused on the MCube aspect, which is the manipulation part, not the vision, because Jen Xiong already talked about that. So let's take a look at the pickers in the Amazon warehouse. This is what I found just in this week. So the pickers in the traditional Amazon warehouse look like this. They are monitored by their speed and accuracy. That almost sounds like a robot in our research paper. And they need to pick about 120 items per hour and also walk for 15 miles a day. That's pretty labor intensive. And the number of warehouses is actually growing. That means the demand of the picker is also growing. In this reporter Bloomberg interview, they interviewed this picker and they mentioned that there's new 1,000 employees on board only on just on that week, and they need to train 190 people just in that morning. And there are 3 warehouses, new warehouses, that's massive Amazon warehouses added in last year, 2015. So the need is growing and the labor is actually pretty intensive. So the current solution from Amazon Robotics, they have the HIVA system like this that brings the particular shelf that contains particular object to the picker. And the picker only needs to stand here. However, the key challenge is that the shelves are chaos. This is a quote from the internet. They need to pack as many objects in each shelf bin so that to minimize the occupied area. And also they don't have much time to sort out the items because there are millions of objects coming in, and they just try to cram them into an empty bin. So picking and stowing are both hard if we are just thinking about the pure suction technique that we usually use in the Amazon picking challenge. For example, picking, it is very hard to just pick one object out of this shelf. And also stowing, how do you stow them perfectly packed together? That's also a challenge. So our group, we think that we need to develop some more complicated manipulation strategy so that we can put it precisely at the point so that it can pack well. So the Amazon picking challenge, we talked about it today. There are picking tasks and stowing tasks. The picking task is there are more objects in the shelf bin. For example, if you want to get a duct tape, you need to get out the mesh cup first. So you need to have a higher level reasoning. And the stowing task, you need to empty this this tote, and put it in a populated shelf like this. So you need to see where it's empty and try to dump it there. And also report where it ends up, because the next time the picker needs to know where it is so that they can retrieve it. So the items are a wide variability, like weight, shape, materials, and compliance. And some challenging thing is the mesh cup that we talked about, that it has nearly no depth massive information. And also the dumbbell is quite heavy if you are just using suction or you just it's also hard to grab. You need to precisely grab at the center of the bar. There are clutters, object may be hidden, and the speed, this year is 15 minutes to pick 12 items. That is not fast compared to the human pickers, but we are gradually improving. So there are many different solutions we saw at the picking challenge. Most of them employ a long suction tube because suction is still like easy to use, and because the shelf is actually very deep, like 40 centimeters deep. So they need the longer suction tube. And usually they accompany with a very powerful vacuum cleaner, and sometimes very actually noisy. The human size is from routers that they can do either suction or grasping at the same time. And there are some teams that has tool changing, like they can pick up, like they have many tools, maybe for different objects, they have different strategy and effector. Some are human looking. I heard about like one team, they bought the flight ticket for their robot so that they can not only work together but also travel together. They also compliant arms so that if human intervene or want to teach something, they won't get hurt that easily. So this is Team MIT solution. So our team, we want to incorporate many different kind of picking strategy, suction, grasping, and some scooping, all inside one gripper, so that we don't need to do tool changing, and also it's more compact. So from low level to high level, it looks like this. Our key contribution is this manipulation. We develop a bunch of manipulation strategy, and that leads to our that guides our gripper design so that it helps us to execute those manipulation strategy. So on the hardware side, we have this ABB robot arm and also a robot controller that controls the robot very precisely and fast. It can achieve like 7 meters per second. And also the gripper is the wise gripper is very helpful. It has position control and also force control. Like it can go through 5 Newton to 80 Newton when you want to pick very heavy object. And motion part, we are also doing very simple. We don't do much collision tracking. We mostly do is just IK solving. There are some guarding moves that uses the sensor on the gripper, so that when you reach down to the toes, you can sense you touch it, because the vision still has some noisy. So we use the tactile sensor to sense it and stop and grab it. And perception, we use RGBD sensing and also many kinds of contact sensing in the end effector. The task planning is a high-level planner that tells like which primitives, should I do suction or should I do grasping? So it is trained using some human labeling. So this is from the other view with a shelf and a tote. This ramp is what we improvised during the competition, because we saw many items that can drop at this point, so it can just slide into it. So let me talk about a system full overview of our architecture. This is the whole overview. We have a high-level planner, like the thinker, the brain, that can trigger the perception. There's a perception primitive that goes and take many views of the bin and do the post-processing. After determining the pose of the object, then it goes on to determine in this pose, should I do grasping or should I do scooping, etc. And there are IK-FAST. We use IK-FAST analytical solution to solve for just the end pose, end joint pose. And it triggers the arm, gripper, suction, spatula. Spatula is at the end of the finger. And also there are feedback sensor. The gripper encoder tells us whether there are objects inside the gripping, or the suction, it has pressure sensor, tells us whether objects are sucked, And Hall effect sensor is something special that can tell us whether the suction cup in contact with the object. And also spatula, it has strain gauge. Like strain gauge tells you if the spatula is bent or not to sense the contact. So perception, I'll go very quickly. We fuse the multi-views because we have this very precise industrial robot, so that we can easily fuse the point cloud to deal with the occlusion situation. So we take 15 views, and actually the processing is during the motion. So when the motion is done, the processing is also done. So everything can be done in about 10 to 15 seconds. And this approach is already described by Jiansheng, but the key thing here is we output the 6-stop poses of every object into this spin, so that we can reason, like for the high-level planner to reason, which primitive to execute. And also the centroid, sometimes we only want the centroid and the principal axis of the segmented point cloud, because the suction only requires a surface, that we can put it at a centroid, then we can suck it. And also a confidence scores, because some object is occluded behind, and in that situation, the confidence scores will be low. That tells us that we should remove some front object and then attack and do the perception again, and hopefully the confidence scores will gain, and then we attack them. And now I'm going to talk about the gripper design, which helps us to execute the motion primitives. So the gripper is actually, we are not very professional. We've done it all in-house. Elliot is the expert here. So in 2015, we have this gripper design, which is mostly passive on the finger. So on the one side, it has very sharp spring steel, so that if you have an object that's flush against the wall or is on the ground that you want to scoop it, so then the spring steel can apply some preload, and then you can grab the thin object. And on the other side, you have this suction cup, so you can turn it and do suction down on the object. And in 2016, because there's a new challenge, the stowing challenge, so that the suction cup probably needs to point frontal and also point down, because like if you're going down, then you need the suction cup to point front. So these are like it's so-called bistable. It can either point out or point down. It won't be in the middle. And there are spatula, which is kind of hard to see. It can extend or stow. So if it's stow, then you can do your suction. And if it's expand, you can do the flush grasping. And we've also put many sensors on the gripper. So on what I said, strain gauge, they are at the spatula. Hall effect sensor to see if there's a contact on the suction cup. Also tell us where it is, like what's the state. Is it pointed forward or downward? And there are gripper encoder to tell us whether there are object inside here. And the real sense cameras here that because it's also like at an end effector, so it can look at many views. And also the other thing that we want to do but we haven't done yet is when we execute the motion, we want to also keep track of it so that it can also close the loop. Like somebody asked about that in the morning. So that will be a future work. And there are suction pressure sensor located inside the wrist. So now it's demonstrating the spatula opening. So it will stow and open. So when it opens, you can go and grab things that is maybe tightly packed so that the spatula can somehow squeeze into the very narrow empty space to grab this object. So I mentioned this suction cup. It's purely passive. There's no actuator. So how do we reorient that? There's a very clever thing that there's a brush here. We are not using it for cleaning the suction cup, but for reorienting. Let me play it again. So if it's go up, then the suction cup point forward. If it's going down, then it's pointing sideways. Okay, now it's a key thing of the motion primitives that we developed. So the first thing are the enveloping grasp. It actually opened the flow spatula and grab the object, and it actually is holding it out. So the spatula avoid the object to tilt forward, to form a very good force closure. And on the tote picking task, we also have this enveloping grasp. So this, I think, is grasping a t-shirt, the t-shirt. So it goes down. It actually uses this suction cup to guard the move. And after it touches it, it closes the gripper and grab it off. So the pinch grasp is for some smaller and short object. Like this is a women's glove. It's hard to see because it's black. But if it's very short, the gripper easily caught on this lip. So it goes in and goes down. Use the very tip of the fat fingers to grab the object. This is playing again. Also, flush grasp. Flush grasp uses the nail, the fingernail, the spatula. Open it and flush against this side wall and go and grab one book. And also for the toe, there's a flush grab, vertical flush grab. There's a pencil set, I would say, and it's flush against one side of the red tote. So you can close the spatula and grab it. In this way, we kind of more certain about the object pose inside our gripper. So when you go into stowing, put it into the shelf, it can be easily tied together. We haven't get to that yet, but this is the first step that we are attempting. And scooping is kind of like flush grab, but it's on the ground. So we open the spatula, turn it sideways, and push the object to the end. Kind of use the end as the environmental finger that helps the object get into our gripper. Now it's suction down. Suction down for object, easy for suction. And the key point here, because we have the passive rotation, that means when it comes out and go down to the tote, because of the gravity, the passive rotation will point forward, so that when it goes down, the object doesn't just shear off because not enough suction force. So this is another for the tote, the suction down for the tote. So also, if you pick it up, rotate and put it into the shelf, because of the passive rotation, the object will shear off. Feel free to ask me questions. And this is suction front for objects that are like too tall, so that you cannot put your finger above and suction down, so you go forward. And you need slightly faster speed so that it can engage the suction cup.
How do we control the friction of the passive joint?
Passive, you mean the suction joint? We just try to tune it so that it's relatively good for the weight range in the object. And this is suction side. Suction side is good for also object like on the side. If you have many books like packed together, then you can have the suction side to just suck one object out. And that's also applied to the bin. Yeah. So that's around 10 primitives, and we have 4. Like now they are expert in these primitives. They tested many times and knows what primitive suitable for which object and with which pose. So with that knowledge, we can feed that into the high-level planner. The high-level planner takes in first the graspability of this object, whether this object is good for this object, this primitive is good for this object. And also for the object pose, if it lying down or standing up, they may be different primitives that are suitable for each situation. And so also we try to encode the clutterness, like maybe object in front, object on the side. We handcraft several features, and then there's a machine learning techniques, like we learn the logistics regression to say like this primitive in this situation, what's the success rate? So this high-level planner will try to maximize the probability of the success rate. And also there's a vision confidence score, so that we can know whether the result is confident or not. We also have the multi-step planning, because there are objects hiding behind the other. So this high-level planner kind of search through a tree. Like now the depth is about only 3 steps, and we compute the probability whether that's success or not. So searching through all the tree and find the maximized path that we want to execute. The paths are like doing suction first on this object, put it in the other bin, and they go and attack the other object. And we have a random scene generator that generates clutter scene, and we let the human labeler to say whether in this situation do suction, what's the success rate? Probably 0.25, 0.5, or 0.75 or 100. Yeah, from those we train the probabilistic function. And this is the picking score. This is kind of a result from the competition. We in the picking from the shelf, we actually mostly use grasping. This suction down actually suck the wrong object. And mostly others are doing grasping. Like grasping is kind of reliable in the picking test. Suction has some kinematic issue in this year's design on the gripper, but we can keep on reiterating it. So we end up in fourth place in the picking test. And for the sewing test this year, we actually mostly just do suction, although we have the grasping also enabled. We just feel that the suction is more like easier to implement, and also like the result is actually quite satisfying. So we take how many objects? 1, 2, 3, 4, 5, 6, 7, 8, 9. We pick 9 objects, and we end up in 3rd place.
Well, what does the bad result mean in the previous slide?
Which one?
You have negative score.
Yeah, so if you pick the wrong object, and you report the wrong thing, then the wrong object not in the bin, and also wrong object in the tote, then that's minus 10 times 2. Yeah.
So what's the difference between picking and storing? Because it seems like section works on one and it doesn't work on another.
Yes, I think that's basically the gripper design. So we can take a look at the. So last year actually the suction works well because it's on the side. So we can use the force control of the gripper to open and to avoid the collision. But now if it's at the side, then, and also we have a camera here. So it's easy the camera will hit the shelf or other object. So that's why this year the suction strength, I would say, is strong, but the kinematic issue is slightly harder. Yeah, we realize it like very toward the end, so we cannot change it that much. Okay, so that's almost the end. The summary is that we have a versatile manipulation system. We try to explore more because that's our expertise in our lab. And we try to develop our gripper so that we can execute these manipulation primitives successfully. So there are slightly minor things that we try to exploit the robot accuracy so that we can do it good for the picking motion and also for the multi-view for the perception. And we have a very structured system. Like if you have a new primitive come in, we can also expand our system. So we are always thinking about this real problem that like you cannot just deal it with pure suction or pure grasping. There must be a combination of those things. So yeah, that's the end. And we like to have open loop execution. Like in this situation, you kind of need to hold down the band and see how the band goes, and then planning it online based on the perception, and then grab it.
That's closed loop.
Yeah, closed loop. Yeah. So moving forward, we would like to have a physical simulated environment so that we can have a lot of training data and also a lot of testing. So that the hard thing for training and testing in this physical world is you need to reset. And also you need to avoid collision, because after collision something breaks or the shelf moves very far away for using our industrial robot. And also benchmarks, because the perception system and also the high-level planner is kind of a data-driven approach. So we need to have a good benchmark, a good data set with good ground truth to evaluate it so that we can tune it to the best performance. And also close the loop, we want to use visual to track the object while doing the manipulation and also do tactile servoing. More iteration on the current gripper. We are pretty aggressive, I would say. We put lots of sensors, lots of actuators in the gripper, but many times it fails. And we want to try to simplify it and also strengthen every component so that it works well together. And some more higher resolution, like 2D tactile sensing, the gel site, which has a camera that look at the gel to see. Even you can use that to detect detect the features on the object that you are grabbing. So, and stronger suction, stronger spatula, that's like need to have some experience, like testing and iterate on that. So that's the end of my talk. I welcome your feedback and question. Thank you. Yes.
So you use multiple views, right?
Yes.
To get the 3D model and all that. So is the robot arm pretty precise, or you have to use visual features to actually track them?
So the arm is actually pretty precise. Like it should be around 1 millimeter accuracy.
0.1,
0.1.
absolute accuracy 0.06 or 5 repeatability.
Yeah. So what you find
a very high manipulator like KUKA, you can't do a cheap manipulator.
No, yeah, these are cheaper one. Intelligent switch KUKA version we refer to DLR, that's the expensive one. But all the other KUKAs are similar to this. But I'm not sure the accuracy of that expensive one, because it has the compliance and all the others.
Yeah, Remus is from ABB, and you can talk with him more. But what we find out is actually the visual, the real sense, the camera intrinsics is actually not accurate. Like the 10 centimeter it reports is actually different from the real 10 centimeters. So that's the real challenge. And we use ICP kind of approach to fine-tune the pose so that it can aggregate well.
So you're aiming for a very versatile end effector to really cover many different cases, but at least according to my experience, every time that you're adding one new modality, you have to duplicate all the work to provide this modality, and then you might have to go back to the high-level planner and change it again, and this requires a lot of software engineering effort and then a lot of integration. How much was this an issue in your experience?
So for the integration, because a high-level planner, we just provide the new probability table that how this primitive against all the object, what's the success rate? Just try to provide that table, then we can extend that. So, but on the hardware part, as you said, it may need to redesign a little bit of the gripper.
Is there a benefit of putting everything in the same arm versus perhaps putting?
Yeah, that's a good question, because we only have one arm, so we try to put everything in one, and also avoid like any changing. Like if you have dual arm, like one reachability is probably cannot cover the whole shelf. Yeah. So that's, and also one arm is actually faster than I say.
During the competition, do you have cases that the objects were behind, they were obscured? Can you comment on this?
I think so. I'm not sure about the particular case for the real challenge, but in the practice round, we do have this kind of cases, and we do actually successful pick in some case, because there's a challenge that because you need to successfully pick two objects, the one in the front and also the one in the back. So I wouldn't say the success rate is high, but it can plan that kind of plan. Yeah, and we will iterate on that.
You have defined a lot of these primitives, and I was wondering for each of these objects, you need to define this primitive, but if there's a new object that you have never seen before,
Yes.
how do you choose this primitive?
So,
or in other words, do you have any learning concern in your whole system, or this is still the missing link in your whole system?
so the way that we do it practically is that like we have the four expert people that work on each primitive, and if you have a new object, they see it and they kind of know like the probability. of this primitive success rate on that object. Then they put on the probability for each object what primitives work. Then the whole thing still work.
But I think this primitive can be learned from this data-driven approach, or if you have like if you use some feature from the object like the image or other features,
Yeah, like the automating this process. That's also one of what we are thinking of, and it's on the to-do list. And it's also, I think, it's a very good research problem. Yeah.
So do you plan to do it in simulation or?
No, we didn't do any simulation here. Yeah, because the real world, the physics world, the friction and many things that like gazebo or these simulation doesn't really work. Like gazebo probably doesn't have a suction thing inside the gazebo. Yeah, I think that's
Suction, it's not going to be with all the fluid and sucking. It's not an easy problem.
Yeah.
Simulation.
Okay, thank you.